So, so that what is the difference between carbon and proton NMR spectroscopy? The main difference is that the 1H NMR, 1H, this is NMR active. Its abundance is 99.9%. For 13C, its abundance is 0. Sorry, 1 point almost 1%. That's the main difference. Means this spectroscopy, for this spectroscopy, we should take very low amount of samples, low concentration, it work. As the abundance of 1H photon is 99.99%. Here we need higher concentrations. Another thing that, let's say we are recording 1H in our spectroscopy. This is the carbon. So CH bond. So the chemical shift of these protons is influenced by the electron of these bonds. Means the chemical shift is influenced by two electrons, two bond electrons. These two bond electrons determines the chemical shift of these protons. Determines the chemical shifts of the proton. Chemical shift. On the contrary, for 13C, let's say it's a 13C, we have 4 valency, that is the 8 electrons together determines the chemical shift of this 13C. Here is the 2 valence electrons or bonding electrons, here 8 electrons. 8 electrons determines the chemical shift. Chemical shift. As a result, if you look at the proton NMR spectroscopy, the chemical shift range is very low. Start from like 0 ppm to it ends around 11 or 12 ppm. Because this chemical shift range only depends on the two bond electrons. That's two electrons. They are the main factors. But here, the 8 electrons. That's why its range is very much high. Starting from, let's say, just 1 ppm. If I just here put the 0 marks with 0 ppm, it almost goes up to 220 or 230 ppm. This is one of the fundamental difference. So this is the difference number 1. This is difference number 2. That here two bonds electrons determines the chemical range of chemical shifts. Here 8 electrons determines the range of chemical shifts. Number 3 is that from proton NMR we can quantify the number of protons. So 1H NMR spectroscopy can determine or can quantify the number of protons. Why? Because you know that 99% abundance. If this is 1H, that is also 1H. That's why. For example, this is CH, this is CH. If this is one protons, there is 99% probability this will be another H, not D. That's why it can quantify the number of protons. But for carbon, only 1%. If this is 13C, the next carbon will be 13C. The probability is like 1.1% because its abundance or less than that. Or less than that. That is the probability. If it is a 1 carbon standard, the next will be the 1 carbon. That probability is very low. That's why, because it's just only 0.0 something very low percentage. That's why the proton NMR spectroscopy or 13C, sorry, carbon NMR spectroscopy, 13C NMR spectroscopy cannot quantify or cannot indicate or cannot dictate the number of carbon. If some basic question is asked on the differences between proton and carbon, the first is that abundance is very high, that's why it works at very low concentrations. Abundance is very low, that's why it works at very high concentrations. So its range of chemical shift is very much low, very low, 0 to 12 ppm. It's quite higher because the fate of chemical shift is determined by the 8 electrons. Here it is 2 electrons. One NMR spectroscopy can quantify the number of protons as if this is hydrogen CH2. There will be NMR active CH2. This probability is 99%. That's what it can determine. But 13 cannot determine the number of carbons. It would determine if the availability of carbon would be very high. That this is 113C, next one is also 113C. So if this is 1, next is 1. But it cannot. If this is 1, the next is 1.1%. That's why it cannot dictate the or explain the or quantify the number of carbon. That's the basic difference between the carbon and protons. And why we are going so details of theory? Because again I repeat, every day I tell the same thing. The question pattern is going to change. If you know, you can answer. If you have the concept, you can answer. If you don't have the